Alright, I want to look at a decoding circuit now, and this is not too different from what we would do with regular digital logic, but it's a very useful circuit. The idea of this is to build a line of cells, a vertical line, and allow us to send a bit pattern into the west, and we pre-specify what pattern we want to match with this column. For example, we might say 0, 1, 0, 1, 1. And we want the output on the bottom to be 1 if and only if the inputs on the left are 0, 1, 0, 1, 1. So it's called a match column, and it's a way to detect a certain bit pattern and send a signal out if we detect that pattern. And doing this is extremely straightforward. We basically need two types of cells. One is called an equal 0 cell, the other is an equal 1 cell. So here's what an equal 0 cell looks like. And we have to do two things. We have a bit value coming in from the west. We're going to send that out to the east because we may have multiple match columns here. We're also going to take the value coming from the north, and we're going to AND that with the inverse of the value from the west. And that's going to be our new value to the south. Our equals 1 cell is going to be almost exactly the same, with one small twist. We're going to AND the value coming from the north with the uninverted value coming from the west. And so this is really just making a big bunch of AND gates. Basically, we're going to take a 1 coming in the north means that we've matched everything above this cell. And if we are looking for a 0 and we get a 0 over here, that 0 will get inverted to a 1. ANDed with the 1 means we're still matching. We'll go down to the next stage. If we're expecting a 1, that 1 will get ANDed with the 1 and we'll get a 1 out. If, however, at some point we don't match, for example, we had a 1 coming in here, the output of this AND gate will be a 0, and all the other columns will fail to match. Even if we match the bit coming in, the fact that we have a 0 coming from the north will cause a 0 to come out from the bottom. So at the bottom of a column of these, if any of these bits is different from what we're looking for, the column will output a 0. If and only if all these bits match what we've specified, the column will output a 1. And for the top cell, we need to do something special because we don't have an initial 1 coming in. So we could either feed a 1 into the very top cell, or we could use a special cell, which we can just designate as equals 0 star, meaning that we're going to use this only in the very top of the cell, and we're going to do two things. We're going to take the value from the west and send it to the east, and if we're looking for a 0, we're just going to invert this and send that to the south. And our top match cell equals 1 star is just going to take data from the west to the east and copy it straight down to the south. So we build our columns out of this, and we can detect from the bottom of a column when we find a 1, we know that column matched the particular pattern. So in general, what we do is we lay a bunch of cells out side by side, and we have a signal coming out of the bottom of each of them, and we have different patterns. Of interest to us. And so here's a circuit where we put in a bit pattern of 5 bits, and if it matches any one of these bit patterns, we'll get a 1 coming out the bottom of the corresponding column. We can use that signal to activate some sort of circuitry, and so this is an easy way to drive a state machine, for example, or to move through a cell library by feeding a counter into here and arranging these in binary order so that each time we increment the counter, we get another signal coming out of the bottom, which we could use to select another set of cells that we want to use to configure some target area. So that's a useful circuit, and again, these are just called match columns, or just match col. So there's a video online that shows a simulation of these, and that will probably help illuminate how these things are actually laid out.